Okay, so first of all, quadratic formula. Here's the quadratic formula, and this is what it tells you. It tells you where the quadratic function ax squared plus bx plus c is 0. Okay? Every quadratic function is of this form. Now, if y equals x squared plus 5x plus 6, then y is x plus 2 times x plus 3. And the only way this function can be 0 is if x is -2 or x is -3. Because the only way the product of two numbers can be 0 is if one of them is 0. Make x plus 2 0, x would be -2. Make x plus 3 0, x would be -3. Quadratic formula. X squared plus 5x plus 6 is of the form ax squared plus bx plus c. A equals 1, b equals 5, c equals 6. So we conclude that y plus 5x plus 6 is 0 if and only if x equals -b, which is -5, plus or minus b squared, which is 5 squared, minus 4ac, which is 4 times 1 times 6. All that over 2 times 1. Down wrong there. This over here is just the square root of 1. Then you plug it in and everything comes out. You've done this before, so I don't think you have any problem solving this. Remember the formula and remember what it means. So what's this tell you about the graph? Means that x equals -3 and x equals -2. The graph is, well, the value of the function is 0, so y equals 0. Okay, remember that the quadratic function tells you where y equals this thing is 0. So it tells you where this expression is 0. So your quadratic function is going to be 0 here. So the function, the graph of the function has to go through this point and this point. The end behavior of this function is the end behavior of x squared. X squared has a graph that looks like this. As x goes to infinity, y goes to infinity. Okay? X goes to infinity if you go this way. Y goes to infinity if you go this way. This thing keeps getting steeper and steeper. So x approaches infinity as y approaches infinity. Y approaches negative infinity if you go this way. Y still goes to infinity. So you've got a graph that goes through these 2 points. It goes to infinity this way and infinity this way. You can indicate that by an arrow this way and an arrow this way, indicating that it goes up this way. You can also find the y-intercept. Okay, the y-intercept occurs when x equals 0. Y-intercept occurs when x equals 0, so you plug in 0 for x, and that leaves you with 6. So the y-intercept is at 6. So let's just say that's maybe here. And that's the point 6, 0. So the graph has to come down here, come down this way, through here and back up here. The vertex of the graph occurs halfway between the zeros. Now, this function is just your x squared function, shifted to the left and shifted down a little bit. You take the basic x squared function and you shift it 2.5 units to the left, halfway between the zeros here, and a little bit down, and you have the vertex. The axis of symmetry is the line x equals -2.5. The vertex is on the axis of symmetry. Make sure that I'm seeing this on the string. Yeah, vertex is on the axis of symmetry. Instead of -2.5, I'm going to use 5 halves because I've got to do arithmetic with it. Okay. Now remember, this is a function y equals f of x, and let's write it that way. So that I can use f of -5 halves as the y coordinates, right? Because y is f of x. So when x is -5 halves, y is f of -5 halves. And f of negative 5 halves, you just plug in 5 halves in for x, so you plug 5 halves in for x equals then plug it in. It's going to be 25 halves minus 25 fourths, or minus 25 halves plus 6. And that equals 25 fourths minus 50 fourths plus 24 fourths, which is negative 1/4. Okay, well, now we know that the vertex of this thing is right here, the low point, which tells us, among other things, that this could be obtained in the basic squaring graph. We don't need a vertical stretch because this is x squared and this is x squared. I don't have time to explain that, but it's explained earlier in the course. The bottom line is, if you shift this left 2 units and down 1/4 of a unit, you get this graph. So we have this. Graph is a graph of a basic squaring function, y equals x squared. Shift the negative 5 half units in the x direction. Negative 1/4 unit in the y direction. It follows that f of x is x minus negative 5 halves squared minus 1/4. Which is x plus 5 halves quantity squared minus 1/4. So this is another form of this. Here we can say that this equals this. This is your vertex form. This is your general form. And this is a big deal. And again, this is called the vertex form. There's another way to get the vertex form using completing the square. I don't know if that's going to be covered, something that should know from prerequisite courses, but nobody ever does. Okay, that's a pretty good synopsis of some of the basics of quadratic function. Since we have to cover like 4 sections today, so you do your homework tonight. Okay, we just cover 2 because you said you're not too bad a shape for 2 of them. We're going to let that stand for right now. We might come back to it if we have time, if you got questions. Let me pause this and see if you do have questions. Okay, Carmen doesn't want to be focused. We'll get a phone. That's it. There we go. Okay. So y equals 0. This is function. This is y. Y equals 0. Obviously, x is 3. That gives you 0 here, right? Multiplied by the rest is 0. If x equals -4, gives you 0 here. If x equals 7, you get a 0 here. Okay. Any of those numbers, the whole thing is 0 because our numbers are all multiplied. One of them 0, the whole thing is 0. X is this, or this, or this, y is 0. Meaning your graph is going to be 0 at x equals 7, at x equals 3, and at x equals -4. So here are your 0. So it has to go through these points. Also, if x equals 0, y is 84. Which means that we also have the point (0, 84) on the graph. Now, if we expand this, expanding it, we multiply x minus 3 by x plus 4 using the distributive law. And we get this, which is still multiplied by x minus 7. And then using the distributive law, and of course I'm not going to write out all the details because we kind of emphasized those details earlier in the course, but I'll say x times x gives you x cubed, that's the only x cubed you're going to get. Now, x times x gives you x squared. X squared times -7 gives you -7x squared, so we have -6x squared. Negative 12 times x gives us negative 12x. And x times negative 7 gives us negative 7x. So we get negative 19x. And then 12 times 7 is 84. Leading term is x cubed. That's the highest power. And of course, you're going to want to look back at section 3.1 and understand that, okay? And understand why this leading term, as x approaches infinity, becomes dominant over all these other terms. But the behavior of the leading term, the highest power term, determines the long run behavior. Oh, it's messing up and so am I. That's his leading there. What's the long run behavior of x cubed? Well, that's x cubed. Looks like this. Okay, so as x goes to infinity, x cubed goes to infinity. As x goes to negative infinity, x cubed goes to negative infinity. You go this way, it goes way down faster. Okay. So now we can show our long-term behavior. Now the graph's going to kind of swap over my sliding over here. Long-term behavior is it's got to go up fast here. It's got to go down fast here. Now that's beyond the interval where all the zeros are. Where all the zeros are, of course, the function, the graph has to go through all three of these points, and it also has to go through the Y-intercept. Well, that happens. This graph looks like this. Comes down from huge negative values, comes up through x equals 4. So it comes up a little higher here before it comes around and goes through this. Comes down through x equals 3. And then back up. This has all the behavior it needs to have. First place, polynomial graph has to be very smooth. No jagged edges, no sudden change of direction. And I swear that it looks like the screen is blurry again. I'm not sure why that happened. Let's see if I can get it to follow my hand and actually focus over here. Are we focused? It has an autofocus, which is great when it works, but it's not working. I'll have to mess with this thing a little. Okay. There we go. Just jog it a little bit. I'm still learning about this thing. Had it for a few weeks. Okay. Okay, well, that's what a graph looks like. Very simple. Okay. Okay, so let's take the same expressions. All this geograph. Now I've squared this x minus 3. Now if we do the same analysis, we still get zeros when x is 3 or 4, x is 3 or negative 4 or 7. So we have these points on our graph. The y-intercept okay, now it's 3 squared times 4 times negative 7. 4 times negative 7 is 28. 9 times 28 is 280 minus 28, which is 252. So I think that's negative 252. We'll pretend that I did the arithmetic correctly, but I did it quickly and I'm not going to check. Big deal is that the y-intercept is now negative. Why is y-intercept negative? When it was positive over here with the same terms, except we squared one of them. Well, the term we squared was negative with x equals 0. So we got a negative here, a positive, and a negative here. Now that we squared it, this is positive. Okay, and this is still positive, and this is still negative. So we got positive, positive, negative. That's going to give us a negative result, as you can see in the arithmetic. This changes the y-intercept. It's at 0, negative 252. Obviously, the vertical scale on this graph is not the same as the vertical scale on this graph. Because 252 is 3 times as big as 84. So this distance on this graph is 3 times this distance on this graph. I didn't want to use the same scale because I had to extend the graph down below the bottom of the platform here. Okay. Now what about our expanded function? Okay, well, expanded x minus 3 times x plus 4 times x minus 7 equals x squared minus 6x plus 9 multiplied by x squared minus 3x minus 28. And that's going to give you an x to the 4th, because you have x squared times x squared, right? And then you'll have an x squared times negative 3x and a negative 6x times x squared. So that looks like it gives you negative 9x cubed. Of course, when you multiply x squared by multiple x, you get an x cubed. And plus some other stuff, and minus 252. And the stuff in between here doesn't matter. The negative 252, of course, tells you that if x is 0, because all these, this will be an x to the 4th, x cubed, there'll be an x squared in an x term. If you do the distributive logarithm, you should do that. I mean, you should know how to do that. You can see how that's going to work out, at least, even if you can't get all the numbers in your head. The negative 252 tells you if x is 0, the y is negative 252, which you already know from having done this, but it's consistent. And the leading term you might not be able to read what I wrote there, but it says leading term. There's your y equals x to the fourth. Graph of y equals x to the fourth. And you can easily graph this if you use standard x values, -2, -1, -1/2, 0, 1/2, 1, 2. Plug in and construct yourself a graph. It's going to look a lot like the squaring function, except it's going to go up faster here and it's going to flatten out more here, as opposed to a parabola, which would have a much less flat vertex. Okay. So as x goes infinity, x to the fourth goes to infinity. What does x to the fourth do as x goes to negative infinity? You go this way, it still goes to infinity. It doesn't go negative, it goes positive. So now we know our far left and far right behavior is like this. So now the question becomes, how in the world do you sketch a graph of this? Okay, remember, the only way you can go through the x-axis is when y equals 0. And the only place y equals 0 is at -4, 3, and 7. You can't go through the x-axis anywhere else. And you can't go through the y-axis anywhere else. Because, of course, this thing's a function. We know its value is here. You can't have another point on the y-axis up here. You fail the vertical line test. You wouldn't have a function anymore. Okay, well, this complicates the issue because we try to do what we did over here. But coming up from down here, we go through here, that's fine. We come down here, we come back up here. And then maybe, we turn around and we come through here. Now we're stuck. We can't get back through the x-axis to go up toward plus infinity. So that doesn't work. Okay? You can't do it. Well, it turns out that in the vicinity of x equals 3, the x minus 3 squared is a quadratic function, right? X minus 3 squared is just your x squared function shifted over 3 units. Well, that gets us around the problem. The other thing is when x is close to 3, x plus 4 is positive and x minus 7 is negative. So when x is very close to 3, it's multiplied by a negative number, which reflects the graph through the x-axis. Whether you understand that or not, that's the reason, at least one way of expressing the reason, that the graph of the function actually does something more like this. And down through here, that's kind of okay, but when it gets up here, it acts a little bit like a parabola for a short time. Okay. Now the x minus 3 squared almost makes the graph almost parabolic here. Just in this little region. And of course, that achieves what you need. You can now draw a smooth curve. It's 0 here, 0 here, and 0 here. And the negative or the 3, 0 point is the vertex of that almost parabola. Now I could go into a lot more detail on that and often do, but that's what happens. Okay. Now we say this is a 0. Of multiplicity. 2. Because it comes from a quadratic function, a function of degree 2. Remember, the degree of a polynomial is the highest power. If you have a quadratic, like, this is a quadratic. This quadratic has degree 2. This quadratic has degree 2. When you multiply them, you get degree 4, because the highest degree term here and the highest degree term here give you the highest degree term here. All right. Anyhow, you have that. You have a 0 multiplicity 2 at this point. Now, zeros can have other multiplicities. You have multiplicity 3, in which case the graph would behave like this near the 0 point. You have multiplicity 4, in which case the graph would behave like this, which would be a lot like this, but a little flatter as it goes through the 0. Okay? And you're going to read about that. You're going to have problems that ask you to think about that, but that's the basic picture of the graph of a polynomial. Now, sometimes you're given a polynomial in this form and you have to factor it. Now, you haven't gotten yet to the techniques. Actually, you kind of have in sections 3, 4, and 3, 5. I think section 3, 4 tells you that if, as in this case, 3 is a 0, x equals 3 is a 0, means if you do a long division of x minus 3 into this thing, it's going to come out even, okay? And then you'll know that it's, well, you done long division? Just say yes or no. Don't use your voice if we don't want to be able to identify you. But you did a good job of describing your voice there, because you have this incredibly high-pitched, squeaky voice. How did you make it sound like that? Okay, well, anyhow, I mean, if I do this, okay. This way, yes or no, you know how to do this. Okay. Yeah, I'll do it real quick. You get x squared, you get x cubed minus 3x squared. And that kind of becomes a plus, that kind of becomes a minus. So you get negative 3x squared minus 19x. So you have minus 3x gives you negative 3x squared plus 9x. And this is subtracted, this is subtracted, look at that plus and you go away. And you get 28x plus 84. And x goes in 28x 28 times. So you get 28x. You get negative 28x. And that's negative. Okay. Negative 28x plus 84. That subtracts off due to 0. Because of this division, we conclude that this x cubed this dividend here equals the divisor times the quotient. So really, this long division is just kind of like a distributive law backwards, and I can explain that in a little more terms, but we're not going to take time because we're just going to get you enough to get an incredible amount of homework done tonight before it's due tomorrow. Okay? If you understand all this, it should give you a perspective that makes it a little easier to understand what's going on. Okay? Okay. I'm going to pause a second, take another look at the homework assignment in my course. Okay. Consider, okay, we're looking at the degree of polynomial in this graph. Graph of this polynomial, which we looked at previously. Has zeros here, and here. Its Y-intercept is 84. And its end behavior is up here and down here. You can verify all that. If you multiply this out, you have an x to the fifth in this end because you have, if you multiply all these out, you're going to get an x cubed, right? Multiply them by the x squared plus 1, you're going to get an x to the fifth. And then you're going to get a bunch of other terms in between. The end behavior your x to the fifth graph looks a lot like the x cubed graph, but it gets a lot flatter near the origin. End behavior is plus infinity as you go to the right, negative infinity as you go to the left. I've already indicated that here. In other words, what you get from your whole analysis of this function looks exactly like what you got previously. Okay. So you would think the graph looks like this. And you'd be more or less right. Except that because of the x squared plus 1, that does change the behavior of the graph and the shape and the way it changes where this peak occurs, it changes where this peak occurs, it changes the symmetry or near symmetries of the graph in ways that I don't want to talk about, so you can almost forget what I just said. But it changes the graph some, but it doesn't add any more zeros. Doesn't add any more zeros, but it does increase the degree. Now, why doesn't it add any more zeros? It's because x squared plus 1 can never be 0. X squared is always positive. When you add 1 to a positive number, you still get a positive number. It can never be negative. Okay? Another way of seeing that is try to solve x squared plus 1 equals 0, you get x equals negative 1, x squared equals negative 1, so x would be the square root plus or minus square root of negative 1. the square root of -1 is not real. Not a real number. There's no number you can square and get -1. So x squared plus 1 can't be 0 because you can't solve that equation. It can't be 0 by common sense because x squared is always positive, and you add 1 to a positive number, you always get a positive number, and a positive number isn't 0. The smallest x squared plus 1 could be would be if x is 0, and that would give you 1. So x squared plus 1 is always at least 1. Anyhow, it can't be 0. But still, you now have a degree 5 polynomial. It looks a lot like a degree 3 polynomial. Okay. Okay, well, the central idea here is that a degree 3 polynomial, it goes through the x-axis at 3 different points, is going to have to turn twice. Got to turn once after going through the leftmost point to get to the next one, then got to turn back up to go through the third one. Okay, so it has 2 turning points, one up here and one right here. By turning point, we made a point where the function is increasing on one side and decreasing on the other. Okay, well, here's a rule. The degree is at least equal to 1 more than the number of turning points. Okay. Now, I can add a number to the end of this thing and it's still going to be a polynomial. Okay. Which means I can lift this graph up. It's still a polynomial, it'll still be degree 3. I've just got to add some number in the end here. That's not going to change the degree of the polynomial. And I can lift it up high enough that it only goes through 0 once. Okay. If I lift it up this high, if I vertically shift it by this much, whatever this number is, then it's going to move the point where this thing's 0 to the left a little bit. It's going to move this point up. It's going to move this point up. It's going to move this point up. And the whole graph will be above the x-axis, except the part that's below over here. Okay. So I guess I just said it's above the x-axis, except where it isn't. But these 2 zeros are raised up to the point where they're not zeros anymore. Polynomial still has degree 3. Okay. And this is still true. It has 2 turning points, so it is a degree 3. And you might not understand all the subtleties of what I just said, but that rule applies. So anyhow, that's a little bit about why the rule is what the rule is. And the more you understand about why the rule is what it is, the better you are at applying it and remembering it. But one way or another, remember the rule. Okay. So now, how do you apply the rule? Let's say you have a polynomial here. What can you tell me about the degree? Well, how many turning points are there? Just hold up fingers. there are 4 turning points, right? So 4 turning points. And what's this rule tell you? What's the minimum degree? The minimum degree means the degree that it at least has to be equal to, okay? I could have stated this as minimum degree, but I like the more vernacular, at least be equal to. That means that the minimum degree is at least one more. Oh, the minimum degree is one more than number of turning points, okay? So what's the least degree? Give you a second to digest it. Yeah. Okay. I don't know if we still getting that. Yeah. Okay. Can I write it? Minimum degree is 4 plus 1 equals 5. That means one more than the number of turning points. Okay. Now, why is that plausible? Well, if I shift this graph downward a ways, okay. I didn't do a real good job of that. Shift it downward. And let me use a different color then. It shifted downward. We got 1, 2, 3, 4, 5 zeros, right? If you got 5 zeros, that means you have to have, well, let's just say the zeros are at negative 12, negative 8, 1, 5, and 1. Now these are the x coordinates of the zeros. I don't want to take the time to write that out because I only got about 4 minutes left. Okay, but those are the coordinates on the x-axis. Then this polynomial would have the form might be hard to read, it's rough word, but you know, this means you have an x plus 12, an x plus 8, an x minus 1, and so forth. And then it would be multiplied by some number, okay, which we could determine if we knew the y-intercept or a point on the graph. That's a different subject. We don't have time to go over that. It's kind of important. But, let's get you through as much as we can, okay? Okay, so we have this form. And you can verify that this form would have zeros at x equals negative 12, negative 8, 1, 5, and 20. Okay. This is a degree 5. And then on the end, you have whatever these numbers multiply out to. Let's see, 12 times 8 is 96. Now it's negative 96 times negative 5 is 480. And 480 times negative 20. Oh my God. 9,600, maybe. Okay. The point is, this expands into a fifth degree polynomial. This has to expand into a fifth degree polynomial. Well, actually, it'd be 9,600A. We'll do A times all of this. Okay. We can lower this to where it has 5 zeros. Then we can raise it back up, knowing that when it's lowered to 5 zeros, it's a fifth degree polynomial, at least a fifth degree polynomial. And then when it's raised back up, we just vertically shift it back up. That's just going to add a number to the 9,600. Not going to have any effect on the x to the fifth. Well, maybe more than you need, but if you understand that, it helps you visualize and understand what's going on. Again, the bottom line is the rule. Also, I say the form is at least this, meaning there could be other factors like an x squared plus 1 or some other quadratic that can't equal 0. Okay. So we don't know what else might be there, but we know we have to at least have these factors. Okay, so I didn't write that out with complete rigor, so don't take it as a completely rigorous thing. I'd have to add those other factors. I have to add a few of that or something. And so you don't have to worry about that. It'll be a little beyond the scope of what we usually do in this course. There's the rule. You did it right. So I think you'll do it right when you encounter it in your homework. And hopefully that'll save you a lot of time in reading and everything else.